Let me now discuss about equation-based simulation using Octave. This is a very powerful method. It is not based on GUI or graphics-based schematics. It is more based on the equations, the dynamic equations that you obtain as the output of analysis of the circuit or a concept. And it is very useful not only in design but also in inventing new circuits, because you get a lot of more insight into the system or the circuit based on the play of the various variables in the equation. So let me go into this work folder. In the work folder, I have two folders, one a rectifier filter for one phase and another for three phase. We will just look at both these circuits and see how the equation based simulation proceeds. So if I go into this rectifier single phase, I have three files here. One is model.m, sim.m. Both these we have discussed, standard templates. Another file, rectifier.sch, the schematic file, just so that we know what it is that we are simulating. So this is shown alongside here. So now let me open model.m, which contains actually the equations which represent the circuit that I am showing alongside here. So let me bring your attention to this model.m. This is the standard template which we have seen earlier. I'll bring your focus to these two lines. These two lines, one is IL dot, which is dIL by dt, and V naught dot, which is dV naught by dt, or the two state equations which represent the dynamics of the circuit. dIL dot by dt is the dynamics of the inductor current. Inductor here is a non-ideality which represents the lumped track inductance of all these lines, and this resistance R1 is also representing the lumped distributed impedance of all this line. R2 is the load resistance, and this C is actually the capacitor filter. Now consider dIL dot by dt. L dIL by dt will be actually the voltage across this inductor, which is nothing but on one side you have this node voltage at Vs. So I am writing that Vs minus the drop across R1, which is IL R1, minus the output voltage V naught at this node. So that's what I am writing, minus V naught. All divided by L will give you dIL dot or dIL by dt. Now to this I am going to put a Boolean qualification. The current here flows only if this source voltage is greater than V naught. Only then the diodes will be forward biased and will allow permit flow of current. So this Boolean qualifier actually behaves like the diodes here. So only if Vs is greater than V naught, there will be a current flow in this line. The other equation is pretty straightforward. C dV naught by dt is equal to IL minus V naught by R2. So that is what I have written here. So after these two equations are defined, you are defining what are the X dot array, which is IL dot and V naught dot, and the X that is passed as input parameter is defining the IL state, that is the inductor current state, and the voltage across the capacitance state. And these here are the parameters that I have used for the various components. Vs is the node voltage here at S, and it is nothing but the absolute value or the rectified value of the sine wave 325 sine 2 pi ft, absolute value which basically gives the rectified value of the voltage at node S. So this, if we simulate, we will be able to see waveforms at various points. So I am scoping this node voltage Vs here, and if you look at the sim.m, already the state variables will anyway be viewed, IL, V0 and Vs, and simulating for this period of time. So let us now go through the simulation. Let me open Octave. So Octave is opened, and let me go into the work directory and into the rectifier single phase. Let me clear up the command window, and I will do package load lu helper sim. So you have the helper files, scripts loaded to help you in the simulation. Now that you are in the rectifier 1 phase, I will run sim to execute the simulation. So as you see here, the simulation is running for 60 milliseconds. Let me expand this so you get the various wave shapes. So this black here, these waveforms are the inductor current values just before the capacitance node. The red waveform is the rectified input sign, and the blue waveform is the V0, the voltage across the capacitance. So these are as expected. The first current is having a larger peak compared to the others because the first cycle the capacitor is not charged, and therefore a larger current flows to fill up the charge. So in this way you can probe various voltages and currents in the circuit, and you can get the ratings of the various devices even before you put in generic devices or the actual components. And if you are thinking of innovating the circuits, coming up for the same set of equation, different circuit topologies, it is possible because you are doing equation based modeling. Of course, I will leave you to explore this possibility and get more insight into it. I will now go into the other folder, rectifier 3-phase. So it is similar to the single phase circuit, except that you have as input the 3-phase voltages. VA is the A phase to neutral voltage, which is 120 degrees displaced with respect to the B phase and the 3-phase as indicated here. All are rectified, which means there are 3 bridge arms, diode bridge arms, and after rectifying, the dominant one obtained from max VA, VB, VC is the one that will be affecting the rest of the circuit. Look at the equation here, this all remains same, Vs minus IL R1 minus V0, and so also the voltage C dV0 by dt is equal to IL minus V0 by R2. These two remain same. Also the qualifying Boolean flag here, the conduction of current in IL happens only when Vs is greater than V0. So this is a 3-phase circuit, and we can see the waveforms. Let me go to the 3-phase circuit, and I will run this sim file to execute the simulation. Sim. So as you see here, the ripple is reduced because it is 6 times the frequency of the fundamental, and thereby you see a much reduced ripple and improved ripple. Here again, you are encouraged to obtain more insight into the circuit by probing different voltages and branch currents in the circuit. So this is equation based modeling, and the equations directly being used for simulation in the Octave space, Octave environment.